Okay, so we have talked about heat diffusion by random motion, and finally there we derived this equation for heat conduction, basically the flux F, yes, yeah, heat flux given by minus K gradient of T, and the value of this K is 1 by 3 V average L into CV, specific heat at constant volume. Now we will apply these concepts to photons. So basically we will be talking about radiative diffusion of energy, right? Fine. So basically photons. Now talking about photons, if we have to apply them, this V average will become equal to C, velocity of light. Now we already know that U, or energy density, is 8 to the power 4. So the specific heat per unit volume, CV, is basically du dt, and this is equal to 4a t cube. Fine. Now the thing that is left is this mean free path L. So what we are going to do is we are going to obtain this mean free path from the equation of radiative transfer. Now let me write it. So equation of radiative transfer. Basically this equation states that the intensity I nu, let me first write it down, this equation. Okay, so what does this say? So basically this equation of radiative transfer states that the intensity I nu of the radiation beam in a medium without emission is diminished over a length s, by this relation, where you see this kappa nu is basically the mass absorption coefficient, or also known as opacity coefficient, at frequency nu. You see this nu over here, so this is frequency dependent. Now you see the mean free path is basically the distance over which the intensity decreases. So mean free path is the distance, basically distance over which the intensity decreases by a factor of E, right? Intensity decreases by factor E, which obviously depends on frequency. Now if we make a proper average of frequency, then we can write this mean free path L, basically LPH, mean free path of photons, as 1 by kappa into rho. Okay. Now this kappa we will just call from now onwards opacity, not opacity coefficient. So you see, let us then compute this radiative conductivity over here. So if we compute this radiative conductivity, then you will see that its value comes out to be 4 by 3 AC T cube by kappa into rho. So that the radiative energy flux is given by F rad is equal to minus K rad gradient of T, or this is equal to minus 4 by 3 AC T cube divided by kappa into rho gradient of T. Okay, now you see in spherical symmetric star, the flux is related to local luminosity using this relation. Local luminosity, that means luminosity at distance r, local luminosity, sometimes written as small l. So we can now rearrange this equation and to obtain the temperature gradient, and that is basically del T del R is equal to minus 3 kappa rho divided by 16 pi AC T cube into 1 by R square. Or if we combine with the equation of mass conservation, then we can get del T del M in this form, and the equation is again written like this: 3 by 16 pi square AC kappa L divided by R to the power 4 into T cube. So these are the two forms of temperature gradient, either del T del R or del T del M. We can get like this. Now you see, this temperature gradient is required. Temperature gradient, this is the basically temperature gradient which is required to carry the entire luminosity L by radiation. Now it gives the basically fourth equation of stellar structure. So this, any of them, is basically the fourth equation of stellar structure, right? For the case that energy is transported only by radiation. Now a star or a region of star, okay, so a star or a region inside a star in which this relation holds, okay, it is said to be in radiative equilibrium or simply radiative. So radiative equilibrium. Previously we talked about hydrostatic equilibrium, then thermal equilibrium, even local thermal equilibrium, and now we are talking about radiative equilibrium. Okay, but you have to remember that this relation is valid as long as LTE holds. So valid as long as local thermodynamic equilibrium holds. Okay, now this breaks down when the stellar surface, that is the photosphere, is approached, because this is where the photons escape, right? So you remember the condition for LTE is basically this, but when we go near the surface, the mean free path for photons becomes greater than your radius r. Now, so you can say that near the photosphere, the diffusion approximation is no longer valid, and we need to solve the full and more complicated equations of radiative transfer. Now this is a topic of stellar atmospheres, and we are not going to talk about it over here, right? So this is valid as long as this, not valid in stellar, not valid in stellar surface. So you must remember this. Okay. Now, before I finish, it is important that you see in hydrostatic equilibrium we can combine this equation and write using this form. You see, we can write it like this: dt dm is, we will just use the hydrostatic equilibrium equation. You will see. So we can write like that, and upon doing this, you see what we get. T by P and into d log T by d of log P, so that we can define a dimensionless radiative temperature gradient by like this. Log T divided by d of log P and radiative, and its value is basically, so using the relation, previous relation, we can write it down, right? So the value is 16 pi AC G kappa LP divided by m into t to the power 4. This is also very important and you have to remember this. This describes basically the logarithmic variation of temperature with depth. Okay, where you see the depth describes log variation of T with depth, where your depth is expressed by pressure for a star in hydrostatic equilibrium if energy is transported only by radiation. Okay, so remember this. Fine. Now you see the radiative diffusion equation that we have just derived are independent of frequency. Why? Because the flux F has been integrated over all frequencies. Basically it has been integrated. However, remember, when I introduced the equation of radiative transfer, this kappa, this still depends on nu, right? So what I want to say is that this is not proper, because everything else is an average over all frequencies. However, this kappa over nu, this kappa, this opacity coefficient depends on the frequency. So this kappa must represent a proper average as well over frequencies, and this average must be taken in a particular way. So this is our next topic, where we will discuss the taking of proper average for this opacity coefficient, and that is the Rosalind mean opacity. Okay, now I will just talk about it, but let me again I have just written this for you. So validity of this equation of radiative transport, so it will be valid as long as LTE holds and it breaks down near the stellar surface where photons escape, and basically as I was saying, your mean free path of photons is greater than your radius, right? And so you can say that near the stellar surface, the LTE condition doesn't hold and our diffusive approximation breaks down. So these equations, they will not describe the stellar surface. Okay. Yes. Now, Rosalind mean opacity. So this is what I was saying, that in the equation, all the quantities are independent of nu except of this opacity coefficient. So we have to take this in a proper way, this averaging. Now you see, if f nu d nu, it represents the radiative flux in the frequency range, then using this relation, basically we can write this flux in this form. So using this we can write, you see, we have, I'm writing down the result. So we have this result here in analogous manner. We can write this down. This is equation 9, where basically what is d nu? D nu, again I am doing the same analogy. D nu is again 1/3 of C into L, or basically this quantity. Okay, equation 10. Now the energy density, so energy density U nu in the same frequency interval, what is it? Basically it is H nu into Nv for photons. And basically what is this? This relation, this is we are well conversant with. Basically this is the Planck function, right? So this is proportional to basically the Planck function for the intensity of black body radiation. So what about the total flux? So you see, the total flux can be obtained if we integrate this equation 9 over all frequencies. Let us do that. So total flux, you see, is this 12, but now this is equation 1. You see, the same thing, this is equation 1 basically, but with conductivity given by this value. You see the whole thing, that's why it is written like this. So the conductivity is given by this value, equation 13. Now if we compare this with equation 4, then this shows that the proper average of opacity, as it should be, is basically this value. So this is the proper average of opacity. Okay, and this is known as Rosalind mean opacity. This is equation 14, by the way. Now you see the factor 4a cube appearing here is equal to, let me write it down. So basically the factor 4a cube, this we discussed, remember, this is basically equal to right? So that the Roseland mean, you see here, the Roseland mean is basically, you can think of as this Roseland mean is basically harmonic mean. Remember arithmetic progression, geometric progression, arithmetic mean, geometric mean. So this is basically harmonic mean of k nu. With weighing function, del u nu del t. Okay. Note that this weighing function, it has a maximum at h nu of the order of 4 kBt. You can do this yourself. Now we can interpret the Roseland mean in another way as well. You see, the integrand of this equation 14, you see, it also appears in equation 9. Where is it? Here. For this monochromatic flux F nu. And when we combine this with equation 10, with this, basically, then we can get the monochromatic flux, right? Now, so what this means is that the Roseland mean therefore favors. So, Roseland mean, it basically favors the frequency range where flux is large. In other words, 1 by kappa represents the average transparency of stellar gas. Okay. So, represents average transparency of stellar gas. Right. Now, let me talk about the conductive transport of energy. Now, you see, collisions between the gas particles, ions and electrons, they can also transport heat. Under your normal ideal gas conditions, however, the collisional conductivity is very small than your radiative conductivity. So, for normal conditions, normal or ideal gas conditions, the collisional conductivity is much smaller than radiative conductivity. Now, the collisional cross sections are typical. Collisional cross sections are typical of the order of 10 to the power minus 18 to minus 20 per centimeter square. Centimeter square at the temperature in stellar interiors, and this gives rise to mean free path for collisions which is several orders of magnitude smaller than your mean free path for photons. So this means that mean free path it is much less than that for photons. Furthermore, you see the average particle velocity, V average. What is it? You know, 3 kBt by m. This is also much less than C. So normally we can neglect the heat conduction. So because of this we neglect heat conduction compared to radiative diffusion. Okay. However, you see, the situation can be quite different when the electron becomes degenerate. So, if electron becomes degenerate, what happens is that in this case both velocities as well increase and the momentum approach the Fermi velocity, and more importantly the mean free path increase. Why? Because most of the quantum cells of the phase space are occupied, so the electron has to travel further to find an empty cell and transfer its momentum. Remember the Pauli's exclusion principle? You see, so at very high densities, when mean free path for electron is much greater than the mean free path for photons, then your electron conduction becomes a much more efficient way of transporting energy. So in this case, electron conduction becomes more efficient way of transporting energy than radiative diffusion. Now, this is important. When is it important? For stars in the late stages of evolution, where we have dense degenerate cores. When we have dense degenerate cores. And for white dwarfs in which efficient electron conduction results in almost isothermal cores. Okay. So, for very massive stars having dense degenerate cores as well as for white dwarfs. Now, the net flux due to heat conduction can be written as analogous. Okay. So, conduction CD is equal to minus K CD into gradient of T. This is equation 15. So that the sum of radiative and conductive fluxes, sum is what? You can write, let us do the sum of both of them and we will have this. Okay, the sum of both, equation 16. Now we can define a conductive opacity KCD by analogy with the radiative opacity. So, if we do that, then analogous to equation, so analogous to equation 4, we can have, you see, we can write the conductive opacity like this. Then we can write the combined flux due to radiation and conduction in this way. So, the combined flux due to radiation and conduction, we can write it like this here. You see, equation 18. Now, what this result means is that the transport mechanism with the largest flux will dominate. So, the transport mechanism with largest flux dominates. That is, the mechanism for which the stellar matter has the highest transparency. So, with K kappa defined like this, equation 17, we can also incorporate this, right? So with this kappa in equation 17, let me show you here. So we can have something like this, right? Just a second. Here. Yes. So this is what I am saying is that if we define kappa like this, then and we incorporate this, then this equation of stellar structure is basically able to account for both radiative transport and conductive transport. See this kappa here. So we can take into account both conduction and radiation in this stellar structure equation by using the definition we have just derived.